Okay, welcome back. Welcome back, everybody, for the fourth lecture of Intelligent System in 2020. Before I start talking about games and adversarial search, I just wanted to make sure that everything went smoothly yesterday. So I spoke to Frank and he said that he enjoyed the lecture. Are there any things where you think it was unclear what was explained, or that it didn't fit the general story or whatever, that we should still discuss today, or was in principle everything clear yesterday? Yeah?
One question between A and A star.
Yeah.
Why A was not optimal or complete? You have an answer on the spot.
So I think the answer, but I'm not sure whether I understand the question right, and I would be surprised if Frank hadn't tried this answer, is that if your heuristics is not admissible, then you might be taken away from the right path by the wrong heuristics. So the fact that the heuristics in A star never overestimates means that you always keep within the boundary between the real path and the path that you've already taken, and you cannot be guided towards the wrong path. And I think that would happen if you don't have an admissible heuristics. And in that sense, it will not be optimal. I'm not sure whether it's not complete, but I think the fact is that the heuristics being admissible forces you to always be smaller, always be smaller than the real value, and that means that you always choose the right path when you do the picking. Probably Frank tried something similar and didn't achieve the answer either. So. Okay, I will think about it and then I will discuss it with Frank whether that was the right question, the question. Okay, so as we started out on Monday, we're looking into how we can implement intelligent systems, so rational agents that can make decisions on some generic problems. So the trick is really that we look at generic representation of problems and generic algorithms to work on those representations, and not look at individual problems for individual, not individual algorithms, solutions for individual problems. And the class of problems we've had so far were in single-player, single-agent environments. So it was always that we had to solve a problem, but there was nothing else interfering in our environment. And what we see today is that we will have the scenario where we have multiple agents involved. And in the game, it's mostly, or in the games that we look into, it's that we have someone who's competing, someone who tries to win against us. Yeah? So we're not so much looking into games where or a multi-agent system environment where agents together try to solve a problem in a well-spirited way, but we look now at really adversarial search, adversarial games, where my opponent in a multi-agent environment has his own objectives, his own goals. It's also a rational agent, but with different goals. Yeah, so that is what we have seen today. And it's very important that we've seen yesterday in Frank's lecture that the standard, sort of stupid, systematic ways to go through these state spaces by uninformed search simply don't work, because the space is so huge that we don't get fast enough to the solutions. And the good thing is that we now have information, human knowledge, I would call it, in terms of heuristics that can help us to guide the process. And again, these heuristics will play a very important role in the game scenarios. Before we get into how we play these games, let's think for a moment, why is it a good idea to work on games. So first of all, we are now looking at a different type of environment, and that is the one where we go from a single agent environment to a multi-agent environment, which is obviously the one where real intelligent agents usually have to perform in. We're now looking at we have a choice between cooperative or competitive, and we look mostly at competitive agents. So why is it interesting? First of all, it's fun. It's something that you can very easily implement yourself, and you can play against your own agent. And usually those games are built for some sort of human level challenge, which is interesting to do. But they are also hard, and they are hard in a way that is well understood. So we have chess, which is a game which is made for humans. So the complexity is still something that is very challenging for humans, but it's still something where computers can sort of work on solutions. And in the end, it was shown that computers can even do it better. The same holds for Go. It's enormously complex, and the human properties of strategic thinking work very well. And again, this is something that the new computers have learned to do as well. For me, the most important thing is that the advantage of games is that they have been built in a way that you start out with a set of rules that you have to communicate between the players. So it is a very, very well-defined game by definition, a problem by definition, because otherwise we couldn't play the game. So before we play a game, we agree on all the rules, and we discuss all the special cases. So when we started to talk about playing a game and solving a game situation, we know exactly what the rules are, and the situation is sort of predefined from the start. And that is very different to a problem where, like driving a taxi through a city, because there are so many undeterminate variables that we have to start defining the problem properly before we even can get to thinking about potential solutions. And in games, by definition, they all come with a very fixed rule set. And so games were used for AI challenges since the first days of AI. And I guess not many of you are old enough to remember this day, but it really was a historical day for my generation. It was in the late 90s when the thing happened, which many people had said will never happen, and that is that machines became better than humans in playing chess. Nowadays, probably every phone can do that, or every small computer can do that, but at the time it required a huge IBM mainframe infrastructure, huge computer power in order to be able to do that. And then the big day came when Kasparov, which was the undisputed chess champion at the time, played the computer and lost. And lost comprehensively several times. And it was really sort of a shock that went through not only the scientific world, but it was really world news at the time. And that was because chess had been considered for years and years and years, for 50 years, for decades, to be the definition of human intelligence. Nothing could do that, only humans could do it, and it was shown that computers can do it better. Of course, people at the same time said, oh, no, but that is not intelligence, this is just compute power, and that is just algorithms now, because we can do it, so it's algorithms. But nobody will ever be able to do Go, because it's so complex. And then in 2016, you might have heard about it when you already studied or before, that also this barrier fell. And there were, now it was Google, and they developed a game engine for Go, and it comprehensively beat there's no world champion, but who was considered and is still considered the best human player. And it won clearly, I think, all the games, and it was considered, okay, so now humans are not the best Go players anymore. And that, again, had the same effect where people said for decades, Go is too complex, you really need human intelligence, and it turned that computers can do it as well. And there will be a philosophical discussion at the end of the course, how we now define intelligence, and that this shows very nicely that the definition of intelligence in the field of AI has been a moving target. And whenever we achieve it, we don't call it intelligence anymore, or AI anymore. But still, I think these are very nice examples of where in a game the boundaries of human intelligence were defined, or of intelligence in the first place, and where AI has broken it. And both of those examples, by the way, are based on the algorithms that we're going to discuss today. They are, of course, expanded, and there's a lot of extra stuff involved, but the main idea is what we're going to see today. As I said in one of the early lectures, Schnapsen is a sort of different kind of problem because it operates in a different environment. It's also a multiplayer game. I play against one opponent. And here the problem is not the enormous amount of moves that I can make, but it's the uncertainty that I have. So that I have a only partially observable environment, and I only know what 6 of the cards are right in the beginning, and I don't know what the other 14 are. And as they could be in any of the other situations, this problem really becomes very complex. So in that sense, the Schnapsen game is very different to Go, but it's still a very, very challenging game, and it is so far unsolved, I would say. Or there are still papers submitted and accepted at the main conferences who try to solve this game. And it's the nice thing, I think, is also so Go is enormous in the choices you have, but it has this deterministic character, and it has the fully observable character. And here, learning to deal with uncertainty and unobservability is also a very interesting problem in generic AI, and that's why I think Schnapsen is a very interesting game to study for us. So in Search, in the first 3 lectures, we didn't have the adversary, and now we have an opponent. What we had in the Search was a solution. We really had tried to find one path from the initial state to one of the goal states, and the heuristics helped us to find the optimal solution. That's what we saw yesterday. And what you need is some kind of evaluation function that estimates the costs from the state you're in, the board state, for example, to the goal, for example, a board where you win or lose. In games, we will use a slightly different formalization, because in a game, when I make a move, there come many moves from my opponent, because the opponent is after, in a turn-based game, you always have your opponent doing the next move. So here we can't really have one path from the start point to the goal states, but we have to think of strategies, as it's called, because it means that whenever I make a move, then I have to be prepared for any of my opponent's move, and I have a strategy for each of his or her moves to continue in order to win. So we're not talking solution paths anymore, but we're talking solution strategies. We also have a very strong time limit, because nobody wants to play a card game where one has to wait for a week before the opponent plays. I still had a chess partner where we played by posts, ordinary letters, so that was you had quite some time. But nowadays, and in the computer game particularly, that's not what you want. You want a second as a maximum for the thinking time of your opponent, or make it a minute maximum if it's a complex game. So you really have a very strong time limit, and that means that you also have to look at approximate solutions. And the evaluation function, because we need to give some evaluation function to each of the states of the board or the game that we are in, needs to somehow consider the goodness of the game position. And again, here we talk about the heuristic values. And then we start, as we started in research, we start with trying to really understand the environments that we operate in. And this is a typical classification of the properties of games that we know. And I think the two things, the deterministic, non-deterministic questions, are deterministic or whether there's an element of chance, and the perfect or imperfect information game. So on the top left quadrant, we have the perfect information games with deterministic behavior. So in chess, you know the positions of the board. You know that when you make a move with your pawn, for example, you move to a new state, and there's only one new state that you can move to. And you know exactly which state you move to. So if you have an element of chance, like in poker, you make a move, so you decide to take a new card, or you to show your cards, but you don't know what's happening because of the element of chance. So somebody else gives you a card, or in backgammon, you have to throw a dice, and you don't know what element, what the answer of the outcome of the throwing the dice will be. So that is the perfect information one, where we make the distinction between deterministic and chance. Yes?
What is the game Nuclear War?
That is a game that was played in the Cold War, and it was about sending armies between the Eastern Pact and the Western Pact. I think it wasn't the most politically correct one, and I might even have made this up. So to be honest with you, I don't know the game. Yeah, but it's as I said, it comes from the previously. This is based on a slide deck that comes from the book that accompanies the book, A Modern Introduction to AI, and they describe the game. So if you want the details, go to the reader, and they will explain what this is. Yeah.
The fact that the snapshot is deterministic, is that because all the cards in the end are being used, or would it be also deterministic if the start wouldn't be
No, Schnapsen is deterministic, and I will show that later in detail how this is implemented. Basically, what you do at the beginning, you have an element of chance, right? So the cards are ordered in some random property, in some random order, but then on the pile, they are in this in the order, they remain in the order. So there is no uncertainty about the next state. So whenever I play an ace and I get the trump, then it's clear which of the cards will come out. So there is a very explicit deterministic choice of the next state. Yeah. So that's why this is a deterministic game. Unless in Scrabble, for example, I must admit I'm not a bridge or poker expert, and I don't even know what a nuclear war is. I have to admit. By Scrabble, yeah, you make your move, you put down your word, and then you grab and you get the new letters. So you can start again. And that is the element of chance, because it's unclear which will be the next state unless you look at all the possible belief states. So we've moved ahead of my story by already identifying that Schnapsen has an imperfect information, because we don't know the nature of the 14 cards that we can see in the beginning. And it is deterministic, because with every move it's clear what happens afterwards. And there's exactly one state after each of the moves. And then there is the most complicated ones, where we have both an element of chance and the imperfectness of the information. Yeah? And this understanding what kind of problem you're dealing with also makes a difference in the terms of the design of your intelligence systems. Yeah, so up to now we have talked about those perfect information deterministic games, which are so complex because there are so many options. And now with Schnapsen, we'll show later how we move then from the perfect information to imperfect information game and solve this problem, or work on this problem in any case. So we start with a very simple setup, and it needs to be adapted for different games, but the very simple setup for the generic algorithm is that we have two players, and we call the one min and the other one max, and it's a turn-based game. So the way we usually represent all our examples is not the same as we have in Schnapsen, because in Schnapsen you don't have always the same order in the turn, because if one player wins the trick, he or she is allowed to continue, so you might have two max moves. So in the simplified example, we have always an alternating move that we can make, like in chess. It's played until the game is over, and the winner gets an award, so has the number of points that she gets or so, and the loser gets a penalty. And then we organize this problem, we represent this problem in exactly the same way as we had before, as a state space, but then the transitions from the second state to the third state, so when our opponent is on the move, will not be determined by us, but by someone else. Yeah. So the successor function is the list of moves, which are first made by one player and then by the other. So we can specifying them as legal moves by we do a move to a certain stage. And then the terminal test is whether the game is in a win or lose situation. And you can have a utility function, a value that you assign to your end states, who wins, who loses. And in this simplified first example, we have a +1 means that max wins, a 0 is a draw, and a -1 is that min wins. Yep. And then the task of Max is that he maximizes the outcome for the game, and he needs to find a strategy to maximize the chances of winning, to find the maximum value of the game. So this is how you would do that for the tic-tac-toe game, brood, butter, whatever it is in Dutch. Basically, Max starts with the first move, and he has to make a cross or a circle with the winning the game if either the crosses are in a diagonal, the crosses are in a column, or 3 crosses in a row. So I believe everybody should have played this game in its youth, so you should all understand it. And then you can see basically, if you go through all the options, the Max player starts putting the X somewhere. Of course, she has 9 options to put the X in any of these fields of the 3x3 matrix. In the next move, the min player is allowed to put the circle. So again, we get now not 9 options, but we get 8 options because there are only 8 fields free. In the next move, it's X's turn again. So she now has 7 options, and so forth until we reach the end where the board is full, like this one, where none of the min or max has achieved the goal of 3 circles in a row or 3 crosses in a row, a diagonal or so on. So then we have a utility value of 0 because it's a draw. Otherwise, if one of the players gets to the goal of 3 X's in a row, then it's a +1 utility value, so X wins. Or if it's 3 circles in a row, then we have, or in a column, then we have a -1 value. That means that min wins. So now the question is, can we find a winning strategy for Max, so the player making the X's, so that he or she always wins the game that is played? This is now translated into a search problem. We try now to find a strategy for each of the moves for X, so that the chances are highest that you end up in a +1 situation. So that's the task for the partial game, the game of tic-tac-toe, and this is the partial tree. And the real tree is, of course, very big. It's 9 faculty. Okay, so how does this algorithm work? Show you in a minute. Now let's understand how this works for the real Schnapsen. And the real Schnapsen, we now look only at phase 2, because in phase 2 we have the same situation that the number of cards is reduced, and we have a perfect information game, so we understand exactly what are the cards that your opponent has. So basically, player X has a set of cards, player I has a set of cards, maximum and minimum, and then Max starts with playing one of his or her cards, and then the moves of the next level are the legal moves that you're allowed to make in the second phase. So you have to play the same color, a card of the same color. So in this sense, if I start out with the ace, then my opponent has to play the same color 10. So there's only one option for me. If I play that is the same for the jack here. What's happening here? It's not working. That's better. So here it's the same. Has to play also the 10, and also for the queen, the 10 has to be played. If I play this ace, then my opponent has to play the jack of the same color, and so forth. So we have a restricted number of moves my opponent can take. Now it's Max's turn again. Has to play the same color. So there are only 3 options here left. Should be two options left here, 2 options left here, because it has to play the same color, and so forth. And in the end, when all cards are gone, you count how many points have been taken, and then the winner is the one who has more than 66 points. Yeah?
So I just wonder if the exception is a pure min-max game. Or
that's in the phase 2. So in the phase 2, when you have played all the cards of the pile, they are gone, then this turns suddenly into a fully observable, it's not partially observable, it's fully observable now, because if you count all the cards, of course this for most people it's not, but for the computer it is. If you have the perfect memory of memorizing all the cards that have been played, you know which cards are missing, and these are the cards that your opponent has. So in phase 2, the game turns from an imperfect information game to a perfect information game. Yeah, so that's why we now look at phase 2, where the game has a perfect information, and we can just simply play out the min-max algorithm. Yeah?
For pure min-max, the opponent, for example, the main, always want to minimize our max value. But for selection, for example, if our opponent is really advanced AI, they can look further away, and maybe their next move is not optimal in the next turn, but
we get into that. That's part of the lecture. Don't jump ahead too much. Yeah, please. So let's start to look into the min-max algorithm in the first place. This mouse is not doing it. This one. Okay. So the one thing is important, that these things here show the transitions and not the states. It might be a bit confusing. So I gave the images of the cards that are played, but of course you end up in a state where you have 4 cards in the second state, 3 in the third round, but then the slide would have been so full. Okay. So now there's an optimal strategy, and we can calculate this optimal strategy. If we know the outcome, if we know the utility value, we can calculate this strategy for max, even if min doesn't play optimal in its way. So both play optimally. That's now the assumption, and we will later get to your question. But there is a simple algorithm, a very simple algorithm, and that is a minimax algorithm that helps us determine the perfect strategy for these kind of games. Yeah, and that is basically that we calculate the minimax value for a node n if it is an end, a leaf of the tree. So if it is a solution where a goal has been achieved, either it's a draw, it's a win, or a loss, then I can calculate the value. I know for each position, if it's a win or a loss, then I can assign the value, the utility value for this node. If it's not the end of a game, then I can do a recursive call, namely that I say, take the maximum of the min-max value of the successes of the node that I'm in, if n is a max node. So if max is turn to play, then all he has to do is to take the maximum value and then apply this maximum value of the same procedure on the successor nodes, on the children, but then apply it on in a min way. So let's see how this works with an abstract example. And the example in this case is that min starts, so we still want to see whether we can win or not, so whether we can get to a 1 value or not. And basically this is a turn-based game. Again, you start here, min is allowed to choose first, then Max chooses, then Min chooses, and then Max chooses again. And the question is, is there a strategy? What is the outcome of this game? If Min is starting, and these are the end states. So in this state, you get to a draw. In this case, Max wins, and in this one, it will be a draw again. So what do you think? Will there be a strategy so that Max always wins? The question is, how can we calculate it? And the way you calculate is that you have a recursive procedure. You want to assign the value of this node, and you calculate this by looking at the values of the nodes thereunder. And you reconstruct from the bottom to the top. So basically, if you look at these two children nodes, and you see that this is the choice that Max has, what will Max choose in this situation? Will it choose the right, or will it choose the left one?
The right.
The right, of course, yes. So the optimal value that Max can achieve in this node is a 1. Yeah, we agree on that? It can always get a 1 in this node. What can it get in this node? A 0. It has no choice, so he has to play this one card or whatever the game is. So in this node, it will be a 0. Yeah. So there is no better way for Max to get in at this node than a 0. And it will be able to choose a 1 here if it chooses the strategy to go to the right one at this point. Now we go the step back, and now it's a Min choice. Yeah. So here's the Min player. So what is the value that Min can choose at this node? It's very simple. It only has one choice, so it can only be a 1. What is it? Can it choose here? A 0. It has only one choice, so you get a 0 here. It only has one choice here, so it will get a 1 here, and it will get a 1 here. Oh, sorry, no. Here it can choose between this 1 and this 0, and of course it's Min, so it will choose the 0. Yeah? So this 0 comes because Min player will choose this node. Here it has to choose this one, here it has to choose this one, and here it has to choose this one. Yeah? And then we are one level higher, where it's now a Max move again, and Max will choose, obviously, here the right one, and here the right one. So whatever choices Min has done so far, Max will always be able to force it to come to a 1 position. That is basically what happens here. So that's why you get, for each of those nodes, for Max, in this plane, you get a 1. And then it shows that no matter what Min chooses, Max always wins. Because if Min chooses this one, it will be a 1. If it chooses the middle one, it will be a 1. And if it's the right one, it chooses a 1. Yeah? So the min-max value of this node is a 1. So it shows that Max will win. And let's see how this then works out in a strategy. So if Min, yeah, they're all the same for Min, so it chooses any of the 3 bad solutions, let's say the middle one. Then Max, of course, will choose this one. Min has to choose this one, and Max will choose this one. So the choice that Max will do in this specific case will be this one to the right, and then to the left, to the right. No, sorry, to the left, here to the left, this one, and here to the right. And that is a strategy for Max to win the game. If Min would choose, in this case, to go here first, then again, Max would choose here, Min would have to choose this one, and Max could get here again. And for whatever choice that Min takes in this game, we always have a path for Max to choose to get to the 1. That's basically what this minimax algorithm gives you. Okay, so that is the simple general idea of the minimax algorithm. But now, obviously, we have used the 0 for the draw, -1 for a loss, and +1 for a win for Max. But most of the games are more complicated, and they have different values for winning a game or losing a game. So the best example for that is always cricket. So is there any British or Indian people in the room? South African, maybe? South African or?
Bangladesh.
Huh?
Bangladesh,
but also a cricket crazy nation. And cricket has probably the most crazy counting system. So there are 4 different levels you can win a game. You can win by wickets, by innings, by points. There are different ways of drawing, and so it really is a complicated game. The only point I want to make here, apart from a nice interruption of the storyline, is that we have to take care of the ordering of the ways of describing a winning situation and a losing situation. And there's not always -1, +1, and 0, but these can be any value as long as they are some kind of linear ordering, I would say. So in a way, winning by a wicket is higher than winning by some innings. And in Schnapsen, we have winning by the points of each individual game. Then we have winning by 7 games or more if you play against each other. The more points you have, the less points your opponent has. It counts. Anyway, the whole point is that it's too simple to say we have a binary win-lose game, and that was how we ran min-max so far. But what you really want is some kind of utility value. And we use the national numbers here to make it easier. But in principle, these would be situations like I have 66 points and my opponent has 23. So that is a better win than if my opponent has 47. Yeah. So we have an ordering of the winning situation in the utility values. And then the point is, if we have this kind of situation, we can apply exactly the same algorithm. Yeah. So the minimax algorithm, we start with a max player who can make a choice, then min-max choices, and then you end up with the utility values 3, 12, 8, 2, 4, 6. And then the question is, what is the best strategy for max starting out? What is the highest value that he or she can achieve if both play optimally? And it's the second step is a min step. Anybody sees what max can achieve maximally? Yeah. 3. Why 3? The middle one is 2. Go on. And the right one is 2. Yes? Yes. So what all we have to do is to look at the minimal values that min would choose. And then we propagate it up to the next level, 3, 2, and 2. And then max would choose. And you're right, then the best value, the minimax decision is then a 3. So with this algorithm, you can calculate the maximum value that the max player can get out of these games when they both play optimally. And here is a sort of a free language way of writing this down. So minimax maximizes the worst case outcome for max. And algorithmically, this looks like this. So we start out with a minimax decision. If max starts the game, then you calculate the value for the state, which is the root of the state. You assign the value of this by calculating max value for the state. So how do you calculate the max value for the state? You first assign for the value minus infinity, so that you can calculate the max value. And then for all of the successors of the state, you calculate the minimum value of this state, the successor state, and you then take the maximum value of all the minimum values that it would choose them. And here is the recursive call, because here you call the next function, which is the min function, which is applied again on each of the state, where you then choose the minimum of all the maximum values of all the children. And here you call again recursively the same function. Yeah. So if this is clear, then it's clear. If it's not clear, I would really recommend you to take the example of such a tree and just initialize the top node. If you start with the max value, initialize the top value with the stop node. Then you build a list, which is a successor list of the state. you take all of the successors of this, this list, and then you calculate the maximum of all the minimum values for this state. And then once you have found this max value, you return it. And this max value, then you will see that you can only calculate it if you do the inverse calculation with the other value. So if you want a max value, then you have to maximize over the min values. And if you want the min values, you have to minimize over all the max values of the children. It's exactly what I explained in the slide before. And this is the pseudocode for that. And in the practical milestone 2 that you might have started working with, this is exactly what you will have to do first in your implementation. It's very simple. Most of the skeleton of the algorithm are already there. So all you need to do is to call this function recursively so that you calculate the right value. Okay. So these are the main ingredients that you calculate the max value of the state by calling the recursive other direction. Yeah.
The examples so far, it seems like these are all in a deterministic setting. You can also apply min-max using probabilities in an indeterministic.
There will be an example later about that. Yes. So now your question comes: what happens if min doesn't play optimal? So when it's not chooses the best possible value it could achieve, but tries to do something clever. And it has been proven that if min doesn't play optimally, max will do even better. Yeah. So there is really no way of outsmarting this systematic algorithm. Now the properties of this algorithm are maybe as to be expected. It's complete. It's exponential in terms of time, so it's not that good. And we see that this is becoming a problem. Space complexity is quite okay because you always calculate only one value at the same time. And it's optimal. So it's quite a good algorithm, but the time complexity for a real world game, an online game, is really problematic. Okay, and as I said before, this is now the state of where you can start with the second milestone. The first one was just getting you to know and play around with the game engine, and now the first algorithm can be implemented. And really, the implementation that is asked of you is a couple of lines. In the second phase of Schnapsen, because we can only play it on the second phase when we have complete information, we can now apply a minimax algorithm. And it's a perfect information game. It has relatively few nodes, namely only 14,400, because we have 10 cards that are played. In the first, both have 5 cards. In the second, both have 4 cards. In the third, both have 3 cards. So it is 5 faculty times 5 faculty is, as we calculate, 120 times 120 is 14,400. It's relatively straightforward. So start with milestones 1 and 2 today, and tomorrow you can do it in the exercise groups and implement it, and you will see that it works out. And now, of course, the question is, okay, so this is how Schnapsen works. So this is it works for in principle all of these games, and chess is exactly this kind of game. So let's just play a game chess with this strategy, this algorithm, and of course it will not work, and that is because of the time complexity and the space complexity. And for Schnapsen it will not work, the real Schnapsen, because of the uncertainty of the game. So the second half of the lecture will be about taming this beast. So how can we tame the complexity and the uncertainty? And there will be lots of methods, and we do that starting at 2:30.